when a mixture of 0.100 more nitrogen oxide, 0.051 more hydrogen, and 0.100 more water were placed in a 1 liter flask at 300 Kelvin, the following equilibrium was established. So at equilibrium, the concentration of nitrogen monoxide was found to be 0.0620 more, 0.062 molar. We want to determine the equilibrium constant K, and in this case, because we want to determine the equilibrium constant K using concentrations, then what we are determining is actually Kc. Okay, that is Kc. Now, well, when we want to determine the equilibrium constant, we need to know first the equilibrium concentrations. So at the beginning, when a mixture of this amount of moles, this amount of moles, and this amount of moles were placed, so that is at the beginning, so we know the initial moles. But even from the moles, we don't use moles, we use what? Concentration. Remember when we are finding Kc, how do you find Kc? To be the concentration on the what? Products, right? On the products we have got what? Nitrogen gas raised to the power, you just get the number in front of nitrogen gas as power what? 1. And then the concentration of what? Water, isn't it? It will be raised to the power what? This is actually not water. This is what? Vapor. You only get those which are in gaseous state. If you have got any solid or liquid, don't include them in this expression. So this will be raised to the power to the coefficient, right? And then divided by, you go on the reactants. You have got nitrogen monoxide. It's a gas, so we are going to include it to the power 2, and then hydrogen gas also to the power 2. But this case is only found at equilibrium. Remember, when you've got a chemical reaction, A reacting with B to produce, let's say, C and D. So let's say when balancing this, you put A in front here to balance, you put B in front to balance, you put C in front to balance, you put D in front to balance this reaction, because when you're balancing, you put numbers in front, isn't it? And so when you are finding what is called the reaction quotient Q, the reaction quotient is simply a ratio of the concentration of the products divided by the concentration of the what? Reactants. So on the product we have got C, that will be to the power what? Small c, that is the balance ratio. And then concentration of D raised to the power, that's small d, and then divided by the concentration of what? A raised to the power what? A. And then the concentration of B raised to the power what? B. Now, this reaction quotient, this same thing, it applies at any condition. Like, it can be at the beginning of a reaction, at the middle of the reaction, or at the near end of the reaction. But when you reach equilibrium, equilibrium is a state where the rate of the forward reaction is equal to the rate of the back reaction. That means the speed at which this one is forming products, because as you are forming products, the products will also be reacting to form reactants. So a certain point in time, when the speed at which these are forming this and the speed of these are forming this is the same, that is the point of equilibrium. And so that is when we use K, rate constant. So when we're talking about at conditions of concentration, it becomes Kc. But when you're talking about partial pressures or pressures, you use Kp. But it's the same, it's all concentration. But these two are not equal. When you want to relate Kp and Kc, you use the equation Kp is equal to Kc, and then RT raised to the power, change the number of moles. So you get these moles, you add them, minus, you get these moles, you subtract them, and then R is the universal gas constant, which is simply 0.0821. And then you consider at which temperature you're talking about. In this case, it's at 300. So we are able to convert actually Kc to Kp. Now, what we want to find is Kc. we want to calculate the equilibrium constant using these concentrations. So in this case we want to calculate Kc. Of course we are going to also determine Kp there, but we don't know the equilibrium concentrations, do we? No. When the reaction reached equilibrium, we don't yet know the concentrations, but what we know is when the reaction was just starting. So let me write the reaction again. So we have got 2 nitrogen reacting with 2 hydrogen. This is forming nitrogen, right? And the water. So at the beginning, what was the concentration of nitrogen monoxide? We've been told a mixture of 0.1 more nitrogen monoxide, and then these moles of hydrogen, these moles of water were placed in what? 1 liter flask. So we know the moles and then we know the volume. How are we able to determine the concentrations? We know that concentration is what? Number of moles divided by volume. So to find the concentration of nitrogen monoxide, just get the moles of nitrogen monoxide divided by the volume. But the volume is given as 1 liter. And 1 into, you are using always 1 in the denominator. 1 into anything that you put on top will be itself, isn't it? So in other words, in this case, the number of moles is just equal to the what? The concentration. Because we're going to be always dividing by what? 1, the moles, to get the concentration. So the initial concentration of nitrogen monoxide is what? 0.1, isn't it? 0.100. What of hydrogen? The moles of hydrogen, 0.051. So those are going to be also the what? Concentration, isn't it? 0.051. This is in molar because it's concentration we are using. What of nitrogen? We used what? 0.10 more water. Have they given us anything of nitrogen? So we didn't put any nitrogen at the beginning. That means the concentration of nitrogen at the beginning was 0 because we didn't put anything there. And then how much water did we put? How much moles? 0.1, isn't it? Yes, 0.1, and then divided by 1 to convert it to concentration. It will still be molar. So this is called the initial. Now we use what we call an ice table. Ice, where I is representing initial, and then C is going to represent what is called the change here, and then E is representing now at equilibrium what will be the concentrations. The equilibrium. It's okay. Now we've been given, so we've put the initial ones. We only know the initial ones, but in the second statement, at equilibrium, they've given us one thing. At equilibrium, what do we know at equilibrium? The concentration of NO was found to be what? 0.64. So at equilibrium, the concentration here is 0.062 molar. This is only for NO. Now just using this one alone, we can determine what was the change. If at the beginning you had this one, and then at equilibrium you have got this value, then how much did it change? Remember, whenever you are talking about change, it is final minus initial, right? So the final is at equilibrium. At equilibrium it is 0.062, that is the concentration, minus initially the concentration is what? 0.100. So the change, if you subtract this one from this one, you subtract this from this, in other words this one minus this one, you are going to find negative 0.038, isn't it? Now why is it negative? It's negative because the reactants, as the reaction is happening, reactants do what? Always reduce. Okay, so that means even this one, if this is the change, remember when we are talking about chemokinetics, the rate at which these two are going to be disappearing is the same. Why? Because they've got the same coefficients, so their rate is the same, isn't it? So as if this is the change, this is the change of the first one, it will also be the change of this one. The reason is simple: they are having the same number of moles. They are all 2, so they are in a mole ratio of 1 to 1. In other words, 2 to 2 is 1 to 1. So this will also be changing by negative 0.038. Okay, now if it is also changing by this, what will be its concentration at equilibrium? And how do you find concentration at equilibrium? This value, and if you remove it from this value, which is supposed to be, it's supposed to give you this. So in other words, to the initial concentration, if you add the change, you're supposed to get the concentration at equilibrium. So the initial concentration is 0.651. Let's add negative 0.038. It's more like from here we're going to subtract this value. So 0.051 plus negative 0.038, that is going to give us 0.013. Okay, that is it. Now look at this point. It's supposed to be, so the same change which you saw here is supposed to be the same change also here, but notice that it's not the same more. These have got a 2 in front. Let me also put here on water, because they are already the same, they are all having a 2, so it's supposed to be what, the same also with water, right? But water, the change is going to be positive 0.03. Why are we using positive? Reactants increase in concentration. Okay, as the reaction proceeds, products are going to be increasing, while reactants are going to be what, reducing. So always the change for the reactants is negative, while the change for the products is positive. Now if you consider this value here, the mole ratio is different. Here we are using a 2, but here we are using only this value, so it is different. And so for us to be able to find the change for this value here, this very change which is here, we are going to divide by 2. Okay, so let's divide 0.0038 0.038 divided by 2. That is going to give us, the change is going to be positive for this one. Why? Because it's a product, it increases, so we divide it by 2. Okay, that's okay. In other words, the change of this one, just divided by 2, it will give you the change for this one. Now that we've seen the changes, what will be the concentration at equilibrium for this? We know the initial, we know the change. What will be the concentration? Just add the initial and the change. It will be what? Still 0.019, right? And then come here, 0.100, and then add this. What will be the concentration at equilibrium? That will be 0.138. Now that we know the concentration at equilibrium, whenever we are finding Kc, remember at the beginning we said Kc is actually the reaction quotient at equilibrium, and so Kc is going to be equal to, the expression is already there, we already wrote, so I'm just going to go on and substitute the value in that expression. So we are saying Kc is equal to the concentration. These concentrations we use in Kc and Kp are always at equilibrium, always. So at equilibrium for NO is what? Okay, N, first we have got N on top, not NO, right? So N is 0.019. It is raised to the power what? Power 1. And then the concentration of this vapor, water vapor, at equilibrium is what? So if this was liquid water, we wouldn't have used it, so only use those in gases. So this would be 0.138. It is raised to the power 2, and then divide by the concentration of NO is what? We can see here at equilibrium 0.062, Raised to the power what? 2. The concentration of hydrogen? 13 should be raised to the power what?
2.
So our job is just to punch this on the calculator, and if you punch it, that will give you 5.6 times 10 to the power 2. Kc and Kp are considered to be unitless quantities, so you don't need to put any unit. So imagine they asked us to determine also Kp. If you find Kc, you can find Kp, right? Kp is equal to Kc multiplied by Rt to the power what? Change in N, number of moles. In this case, we have already found Kc, which is 5.6 times 10 to the power 2. And then R, that is the universal gas constant, we use is 0.0821. At what temperature are we talking about here? 300 Kelvin. And then raised to the delta N is the change in number of moles. So on the products, how many moles do we have? 2 plus 1, that is what? 3. Minus on the reactants, how many moles? 2 plus 2, that is what? 4. So this is actually a negative 1, right? So that is 0.0821 multiplied by 300 inside there, and then raised to the power negative 1. And then the answer that we get, we first multiply this, we raise it to the power negative 1. The answer that we get, we can now multiply with this value. So times 5.6 to the power 2. So Kp is going to give us 22.7. That will be the value for Kp. And that is how you calculate.